Okay, looks like we're thinning in here more. You're probably watching this on YouTube. I'm trying something new with YouTube. This morning's class in a completely different classroom is, the lighting is really weird. I think I mentioned this the other day. The lighting is really weird. You can't see like the PowerPoint and the screen at the same time on the video, and it's really like, I'm sure it's impossible to watch. So I'm trying something new where I have a very high contrast white on black, and you'll see the slides in a bit. But first things first. So anybody know Professor Shapiro in the CS and education departments? Yeah, he has a new puppy. And oh man, this is a very cute puppy. Okay, this is Jumbo Jr., literally his name, Jumbo Jr. You ready for this? He's like this big. And his little tail goes back and forth. Right? I'll play it again. Listen for the like bark. And he like smiles at you. I really just want to take him home. That's all. Steal him, yeah. Okay. All right. So here's what we're going to do today. How many people in here? How many people have either used in another programming class, programmed with, or heard of a stack before, computer science? Okay, a few of you. That's good. For those of you who have seen it and used it before, it'll be a little bit of review. For everybody else, this will be something new, which is great. Okay, we're finally getting into some new stuff. Stacks are are interesting in that they are actually very simple. I will really not show you much code right now because you have already built a stack by building a working dynamic array. You've built something that can be easily converted into a stack. Likewise for a linked list. So I'm not actually going to go into too much code today. But the bottom line on a stack here is that it's modeled like this. You have a bunch of boxes, and you can put another item in the box, but it has to go on top of the ones that are already in there. And then when you pull them off, you actually have to pull the top one. You can't go and pull something from the bottom. That's how a stack works. Don't worry about the details. We will get into that. Okay, but might be some new stuff for everybody. Okay, yesterday's lab and Monday's lab, I went around to a bunch of people, and it seemed like it was a little more work than some of you guys were expecting in terms of like how to make all the linked lists do their thing. Part of it was that the objects we had were a little bit, they were a little intense. But as far as like getting the linked lists to work, took a little bit of, creativity and a little bit of like writing down where all the pointers go. And a lot of people would get to a point where their program was like segfaulting, and they go, I'm not really sure what to do here, right? So what do you do in that case? The best tool, as far as I'm concerned, is a good debugger. Now, I've showed you a debugger before. I'm going to show it to you again on some real code from one of you guys. I don't know who. But I have anonymized it unless you wrote your name sneakily somewhere and I didn't see it in there. But a code that I noticed when I ran it that it like segfaulted, and the question is, can we fix it? And the answer is we probably can if we go through a debugger. So we'll try that out and see if we can do that. Then we'll do the other standard things, Unix tip of the day, and then we'll go into this idea of stacks. Any questions before I get going? Is anybody still not enrolled in the class? Everybody's enrolled? OK, good. Other classes were a couple who weren't. OK, so the Unix tip of the day. Let's do this first. There is a program on the Linux system called, there's two programs actually. One is called BC, and it actually stands for Basic Calculator, I believe, is what BC stands for. And it's pretty cool, because it allows you to do regular old calculations like 2 plus 3 times 4, which would be what? 12, so 14, right? And it knows about order of operations, and it knows about that. And it allows you to do parentheses, and it allows you to do fun things like 2 raised to the 10 is 1024. But what's also cool about it is it lets you do stuff like 2 raised to the 100,000. Now that's going to be a pretty big number, right? Right? This is like only part of the screen. Let me scroll up a bit. Right? 2 to the 100,000 is a really big number. Okay, if I go up here and I actually select all of this, there's another program. Let's see, called word count, which will actually count all the letters in this if I paste it down there, or all the digits in here, right? And that says there's 30,988, probably 30,987 with the return in there, numbers, digits in 2 to the 100,000, right? And BC will actually allow you to calculate this stuff. Kind of neat. What you can also do, if you do BC-L, it will load the math library. So you can do other fun stuff like square root of 2, right? And the square root of 2 is this tiny little 1.414. But that's not really true, because the square root of 2 is what kind of number? Irrational, right? So it actually should go on forever. Well, what you can do is you can say scale equals 1,000. And then you can do square root of 2. And it'll go bing and print out 1,000 digits for you, right? So lots of precision with this calculator. It's a pretty cool calculator. OK, so you can play around with BC if you want. There's another calculator called DC, which actually stands for desktop calculator. And it's a little different. In fact, BC uses DC behind the scenes, but that's a different story. And with DC, you can type something like 4, 5 plus. And if you print out the answer, it will say 9. You can type I don't know, 6, 7 times, and then print out the answer, and it will print 42. So things are a little different here, right? Now you've got this weird kind of way of doing this. You can also do 4, 5, 6 times plus. Any idea what that's going to turn out to be? 4, 5, 6 times plus? 4 times 5 plus 6. OK, so what would that be? 26? OK, Max? 120. How did you do that?
5 times 6. Oh, sorry, 34. Sorry.
5 times 6 is 30 plus 4. OK, so 34. OK, anybody else have a different one? There might be other choices there. Let's see. It is 34. So it actually did it in this. First it did the 6 times the 5, then it did the 4 plus the 5. So it's a little weird, right? OK, obviously, maybe you've seen this before. RPN, right, which we will get to. But it's an interesting calculator, and there's an interesting way about that. What's one thing? Well, in this case, I didn't show you an example before, but it turns out that you actually don't need to know any order of operations for this, which is also kind of cool. OK, so that's pretty much the reason. But we will see this idea a little bit later in the lecture. OK, but anyway, different calculator, a couple different types of calculators. And I don't know how to get out of here. There we go. OK. All right. So that's the DC and the BC program. DC actually came before BC in the program, when they created them. And they were both in the early 70s when they created these. OK. All right. Eclipse tip of the day. We're going to do a little bit more debugging. So the lab 2, you certainly could have used the debugger. And again, if you want to do debugging on your own in some other fashion, use the command line GDB debugger or debug with the cout statements and carr statements. That's OK, but that's probably not the cout and carr statements. Not really the best way to do debugging. Let me show you, as a recap again, how we might go and debug this person's code, anonymously called student lab 2 project person. All right. Here's what happens when I straight up run this person's code. Okay, this is actually somebody in lab who did this. Okay, here's what it says. It says the winner was Marcy with a time of 1,720 seconds. Then it went to Pigpen, then Sally, then Schroeder, and then all the way down to Snoopy, right? And then the other way around, it said the reverse order was Snoopy, Charlie. So what's wrong with this? Well, first of all, they're actually not in the right order at all, as it turns out, right? Because if you look, actually, let's see. Yeah, there's a couple in here that are definitely out of order. OK, 1250 to 1200 to 1100. OK, if they're backwards, they should have been the other way anyway. And then you get to a 1500. So now you know, oops, we got backwards. So something is going on here. OK, and the question is, how do we go and figure it out? We could certainly look at the code and try to figure out what's going on. But another method is to actually just run what you've got and see what's going on. Not only will that give you a feel for like what the program's doing under the covers, but it'll also kind of maybe point you in the right direction to see what's going on. So here's what I'm going to do. In the insert in order function, which is one of the ones you had to write, I'm just going to put a breakpoint. Let's say I put the breakpoint right in this like if statement, if temp node equals null, and there aren't any nodes yet. Okay? And if I go up and I do the little bug here, right? I do the little bug and I click on that, it will come up with a window. It may ask you to go to this window. And what it does is it starts the program on the first line of code. You can change it to not do that, but it generally starts on the first line of code. And then you can continue the program to where that debug breakpoint was. How do you do that? There's a little like resume button up here that says go keep the program going until you get to the line we did. So this is the line that I put the breakpoint on by double clicking on it. And it says if temp node equals null. OK, so is temp node equal to null? You can hover over a temp node, and it actually tells you. It says, here's all the stuff about temp node. And it says the value is 0x0. Max, what does 0x0 mean? It means null. And it's a null in base 16. Right? But just know that it means 0. If it's got an x there, it means base 16. A 0x means base 16. But the 0 means null. OK? It means there's no node here, which is fine. So when we do this if statement, it will say it is null. So it should go to the, if we do this little button, which is the step over button, it will continue the program until the next instruction in our line of instructions. Gets to the insert before, and we want to go check and see if that's working right. If you did step over again, it would like jump over that function. It would do it and jump over it. What we want to do now is this step into function. Okay? And if I do that, it will go and say, OK, if a node equals null, head equals new node, tail equals new node. Is that good in this case? I don't know if you remember this, but it turns out that's fine, because what that means is basically you are at there are no nodes yet, right? And you're going to create a new node at, you're going to, set your head and your tail to the new node, and that's fine. And then otherwise, there's some other stuff going on here. So it actually looks like the person's doing all right so far. What we can then do is we can say, OK, resume the program, and go back to the go and keep going to the breakpoint again. We're inserting a number of times here in a loop, so it's going to go back to the same breakpoint. But now we're going to be at number, like we're going to already have that first node that we inserted. OK? So let's see. Now we're going to look and say the head is now some value here. Let's see if we can get more details on it. If we click on a runner and then the name, and if you scroll all the way down here, sometimes this is a little hard to understand, but if you scroll all the way down here and things go right, we should see Snoopy in there. So the first one that was inserted was Snoopy. OK, right? That was the first thing that's going to be inserted. Now, remember how the lab works. If you've got a node and it's faster than the one you're trying to insert, you're going to look at the next node to see if it still needs to go in the next position over. Remember that? OK, so let's see if that's what's going on here. If we step over this line, it's not null anymore, so it stepped over that, which is fine. Now we're going to check this out. Now we're going to go through the list and see what's going on. OK. All right, so let's see here. So this person created something called a runner 1. I'm not sure what was going on there. But then they don't do anything else with it. And then later they actually check and see if things are before it. So this may be an issue, right? Because right now you look at runner 1, and it actually has a time of 0 right now. So that's probably one of the errors anyway, right here, right? And you can look and you can go, oh, I see. Right now we go down here and we go, oh, I'm going to now check if runner 1 is faster than a runner. It's not, because we've all of a sudden have the wrong one. Does anybody remember what this should be? In this case, we've got temp node here. And what was the one we're inserting? New node? Yeah, new node. Let's change this. Oops. If new node and then a runner is faster. Let's see if that works. Now, let's see if that fixes the problem here. We're going to just restart it because we fixed a bug. We're going to restart it, rerun it, and let's see what's going to happen. It's hard to see that down here. OK. Uh-oh. Now we've got the results are in forward order, but starting with Schroeder, Snoopy's nowhere to be found. And we're like, so we're getting there, right? Like in some sense, these are all in order. We're just missing Snoopy and some other people, right? So something else is going on. Hey, is that hard to fix? I don't know. Let's debug it again and see. Same exact thing. We're just going to go until we get to the first line. Let me bring this down so we have some more details here. And then we're going to continue. And then we know Snoopy went in all right, so we're just going to continue again. All right. Now let's see what happens with the first runner. Now we're actually, if we check this, we could see we're on a Charlie Brown, which is slower than Snoopy. All right. If basically Charlie Brown is faster than Snoopy, we're going to insert it before. That's not going to be the case, OK? As long as we built that other function, right? So let's see what happens. If this is going to, let's see. OK, it says it's not. It failed that test. So it's going to look at the next one. What's the next one after Snoopy if there's no extra nodes? Null. OK. So what we're doing here is we've said, let's see. There we go. So now we've gotten to null. And now it's going to say insert after temp node. We just said temp node is null. And you can highlight this. What's going to happen if we try to insert after a null? Anybody remember? We can go check and see, but we did it the first time. What did we do? Insert after a null. Null means what? We're at the head, actually. We're replacing the head. We're replacing the list. So this is probably not what we want to do, right? If we're at the end of the list, which one do we want to replace after? I heard it. The tail. Maybe that'll fix things. So let's see. We don't want to insert after temp node. We want to insert after the tail, which we have kept. OK, so maybe that's, so let's see. We can go and run this again and try it again from the beginning here. And results. Snoopy, Schroeder, Peppermint Patty, Sally, Pigpen, Woodstock, Linus, Marcy, Charlie Brown, and Lucy. In the reverse order. Lucy, Charlie Brown, Marcy, blah, 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 all the way down to Snoopy. I think we fixed it. OK? So now, do you see how we can go through one line at a time and check the values at everything and do that? I mean, I've gone through it before. This is one way to do it. You can obviously go and look at your code, and that's a good first step to kind of go through each line of code and say, am I doing the right thing? But it's kind of nice when you can see the actual results. Oh, this node is null right now. If I'm trying to go through this procedure, it's not going to work out right. OK? So you see how that works? Maybe a little bit better? Practice it sometime. Like when you're trying to debug, practice doing this, and you'll get better at it, and you'll get better at debugging. And that's the kind of the point. OK? Questions? Yes? You have to click on the line number, and that will put a breakpoint, which says when you're running debug mode, go to that line and stop, and then tell me everything you know about the program right there. OK? And then you click like the resume, and that keeps going until it hits that breakpoint again. Or you click the step over, which goes to the next one, to the next one, to the next one. If you want to go into a function, you click step into, which goes into the function so that you can go line by line there. You practice it a few times, you'll get used to it. OK? All right. All right, no other questions on that? OK. You will get lots of opportunities in homework 2. If you haven't started homework 2 yet, do it soon. OK? It is due a week from Friday. OK. Stacks. So a stack, as I said before, I kind of gave you the 10,000-foot view of a stack, right? A stack is an abstract data type. OK? What that means, and I kind of went over this on like the first or second day of school of class, but a stack's an abstract data type which says, here is a set of things you can do and what we expect as a return. But how you implement it is your own business. OK? You want to implement it efficiently, but how you do it is not my concern. If I know you have a stack, all I know is that you can do the following 3 things that we're going to talk about. And that's all I know. I don't care what's under the covers. Right? I just don't care about that. Here's the 3 things you can do. And let me draw a little diagram of a stack here. OK? We are going to model this going upwards. Okay, many times in computer science, this is how we model stacks. Think of it this way, though. You can think of it as an array which is tipped sideways, and like there's an address, 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 address. Okay, and I don't care if you think of it like address, 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 address. It doesn't actually matter. However you end up programming it is your own business. But you can think of it like that. This is like an array tipped on its side. Okay? All right. So here's what we're going to do. We're going to put some values into this stack, and we're going to use this this operation called push. Okay? And you place an entry onto the top of the stack by pushing it there. Let's pretend we're using integers. So let's push A7 on this. Okay? What it's going to do is it's going to go in here, and it's going to go. The first one is going to say go here. Okay? That is actually going to be a position called the top of the stack. Why is it the top of the stack? It's the last one we put in. Okay? So that's why it's the top of the stack. Then let's say we're going to put 4 in this stack. We're going to push 4 onto the stack. That's the mentality. That's the operation, what it's called. Push 4. 4 is going to go on top of the 7. It's like any stack, like a stack of pancakes or a stack of coins or whatever you want. 4 is going to go on top of 7, okay? And we've pushed it on there. Now, where's the top of the stack now? It's at the 4, right? So the top actually changes to here. Under the covers, you keep track of that details. You keep track of the fact there's 2 items in here. You keep track of the fact that the next one is going to go here, and this one's the top, etc. Okay? This is how you've got to abstractly think about it. Okay, and then we'll push another one in, 8, and then that would change the top to here, and we've pushed a bunch of stuff on there. Okay? One of the other functions we can do is called pop, which is exactly the opposite of push. Okay? Although it's a little more subtle than that in C++ if you're using the actual stack built into C++. Don't worry about that for right now. As far as you're concerned, pop does this. It takes the one off the top, tells you what it is, and then moves the top down here 1. Okay? So far, so good? If I did a pop again, what value would I get? If I pop now, 4, right? I get 4. Where's the top of the stack now? It's actually at 7. Now, I'm erasing these. In your stack implementation, don't do anything with that. Just leave them there. They're dead squirrels at that point, but who cares? Right? You don't need to like delete. Forget it. Just leave them there. All you need to do is move this little pointer, okay, to point to the one that's on the top now. There's another function called top. Top would right now give you 7 if I'd called top on this stack, but it leaves the top of the stack the same. That's the mentality here. Okay, it says, what's at the top? It's like you're peeking at the top. Okay? If we go back and we have the other elements in here, like this, okay, the only one that you have any access to is which one? 8, right? You do not have access to 4 and 7. Could you build access to it because you're using a dynamic array? Well, sure, but you're not using a stack anymore. Okay? The minute you start getting any other information about this, you have left the realm of stack and gone to some other data structure or abstract data type, right? You've gotten the stack says you get access to the top one. That's it. End of story. Fair enough? OK. Those are the 3 main functions. There's another function in here which is pretty important that is not necessarily considered one of the, like, an absolute necessity, although really in the end it becomes one. Is empty is another one. Right? Is empty would return what kind of value? A Boolean value, right? Which says whether or not there's anything on the top of the stack, like whether or not the stack has any elements in it. Okay? All right. So that's what a stack is, kind of in the big picture. Okay? Because those are the only things that you're allowed to do, you only have access to this top. Okay? This is considered a last in, first out structure. Now, you might have heard that in some other classes before, but it's pretty simple. The last one that went in is the first one that comes off the top. Okay? If the 4 is gone, then it's the 2 that comes out next. So you put 3, 7, 5, 2, 4 in. You have to take them out in the order 4, 2, 5, 7, 3. Does that make sense, given the functions we just talked about? Hopefully. If you're confused about that, raise your hand. You get that? You get that idea? If I have a stack of pancakes, I'm not allowed to go and grab a pancake 3 down. I have to get the top one. And if you're taking them out of the oven, you put the bottom one down, then the next one, then the next one, the next one, you eat the opposite order. Last one you put on the stack is the first one you eat. Good? OK. So that's how a stack basically works. And it's this last in, first out arrangement. And there's other arrangements. There's a first in, first out, which we'll talk about when we get to queues. OK? And there's other ones too. There's first in, last out. You could kind of get around saying this is a first in, last out. In other words, this one's the first one that went in. It's the last one out. But earlier today, somebody said semantically that doesn't make any sense. And OK, if you might have other issues. You could take some others out in some other order. But anyway, in our case, we're going to call it a LIFO, or last in, first out procedure. OK? All right. So this is a pretty limited thing, right? This structure is limited. Right? You can only touch the top, and you only get these 3 functions, so it's not that robust. However, okay, it's really frequently used. And it's really frequently used in a lot of different algorithms and a lot of different like low-level computer architecture sort of ways. Okay? Both the operations push and pop are actually assembly code language. Remember I showed you the assembly code the other day and said this will make your eyes bleed if you try to read it too much, right? Some of those operations were pushes and pops on the basic underlying like machine memory. Okay? Why is that the case? Because this is a really cool structure, as it turns out, and it can be used. It's so simple, and it can be used in a lot of different ways. We implement push and pop at the lowest level possible. You guys are going to implement it at a very much higher level, but they are also implemented at lower level ones. Okay, at the very core of a computer. Some of you guys, if you've done any assembly language programming or know that much about computer programs in general, will know that stacks actually, there is this thing called the stack, which is more or less a stack. You actually can get access to kind of a random way, but it's called the stack. And it's part of every program you'll write. It's built into the program. You don't generally access it if you're doing kind of higher level C++ programming. But if you do any C programming, you certainly use this idea of the program stack at some point or another. It's also built in. So when you run a program, the memory system says, here's your stack. And it's part of the memory system that the compiler manipulates on behalf of your program. So it's kind of neat. Okay, and again, it's very like built into the system. How would that actually be used, right? Like, why would the stack be used? Let's take an example here, okay? Let's pretend that we had a few functions here. Okay, we've got a main function, and the main function is going to, while it's running, call some other function, function 1. So main calls function 1, and function 1 calls function 2, and function 2 calls function 3. And I didn't even put function 3 on here, but let's say function 3 does something and then is done. The stack is actually used to keep the state of what's going on in main when function 1 gets called. In other words, when main calls function 1, the compiler has to set up this situation where all the stuff you're working on gets put aside for a minute while function 1 does its thing. Okay? And where does it put it? It actually puts it on the stack. It saves a bunch of information. It saves the next line in here, where the next line is. Okay? It saves some of the information about the underlying data you're using. Okay? And then when function 1 calls function 2, same thing has to happen. Function 1 needs to be saved so that function 2 can do its thing. And same thing when function 3 gets called. Okay? So this idea of saving the state of the program is based on this stack idea. Anybody know why we use a stack for that? Like what's the idea of, remember, we go back and think about what a stack is. Why does it make sense in this case to have this as a stack instead of some other like array or something? Any ideas? What do you think?
So like when function 3 returns, then the information on the top will be where you are in function 2, and then
Yeah, when function, exactly. When function 3 returns, right, you go to the top of the stack and you say, give me all the information you just saved earlier, and it's returned. And then which one gets returned next? Like, where does it go next when it returns? Back to function 1, and then when that returns, it goes back to function, the main function. And isn't that a stack-based last in, first out mentality? The last thing that went onto the stack was function 2's information, and it's the first thing that comes off, then function 1, then the main stuff. So you see how that works? It's stack-based, right? So it's the idea of you're pushing something on and then pulling it back off. What if function 1 called itself? What would that be called in like computer sciencey terms or math terms? Recursion, right? Did you guys do any recursion in Comp 11? Yeah. Some people said in the earlier class, like, we did this much and it was like not very, like, it was kind of too fast, and next week we will go into a much more detailed and hopefully a little slower, like recursion topic. Okay, so you'll get the idea again. I'm glad many of you have seen it already. That's awesome. You'll see it again next week. Okay, so if function 1 called itself, well, then it would be saving its own state on the stack and then calling itself and saving its own state. And a lot of times with recursive functions, you have to save a lot. You have to call the function a number of times, right? And that all gets saved on the stack. Right? Sometimes you run out of stack space. Okay, what's that called? A stack overflow. Anybody heard of the Stack Overflow website? Based on this idea, right? And that means then basically when you have a Stack Overflow, your program seg faults. I mean, almost always, right? There are very few ways to like stop that from happening if you run out of stack space. There are some ways, but it's not easy, and it's not something you want to happen. And that's only because you have a limited amount of stack space for your programs. Okay? So recursion, while a great idea, sometimes runs into problems when you're trying to recurse too deeply. We'll get into that next week. We'll get into that next week. But you get the idea here, right? What happens to the state of this system, right? We save the state, and let's see. Function main calls function 1, calls function 2, calls function 3, and then function 3 returns function 2, function 1. It's a LIFO pattern, right? And whenever you have a LIFO pattern, you can use a stack. Awesome. Okay, and here it is in kind of graphical terms, right? First thing on the stack is main information. Then function 1 goes on there. Then function 2, function 3, and then function 2, function 1 main. So there's your stack idea. Okay, and that's the kind of the bottom line. First use for a stack was actually this idea of saving your program space. 1946, which is a long time ago in computer programming, like computer theory. Like 46 is like at the beginning. I mean, okay, so they have a couple computers and they have some things, but that's like way back. This was proposed by a guy named Alan Turing. Anybody heard of him before? Yeah, you guys have heard of Alan Turing. He's like a giant in the computer science. Like he's like kind of like an Isaac Newton of the computer science world, right? Tragically died young in life. There were a lot of people who were against him being homosexual. It was bad news. England has actually apologized for the treatment they gave him. Bad news, but great, like amazing computer scientist, right? Amazing computer scientist. Anyway, he called these push and pop bury and unbury. Right? Because you're like burying information and then unburying it, I guess. But somebody else came along and said, let's call it push and pop. Say, OK. But anyway, 1946. This is an old idea, right? Old idea. As I said, you can modify your dynamic array or your linked list to behave as a stack very easily. Well, you just have to limit them, right? Like we talked about this dynamic array. You have to limit them to only work from one end, basically. Okay, you can only add and remove at one end. For a dynamic array, if we want good performance, where should we insert and remove? At the beginning of the array or at the end of the array? And if you do, what's the asymptotic behavior for push and pop? Think about that for a sec. What do you guys think? Ethan? Towards the tail. So let me erase this. Do you guys know when I said this joke earlier if you watched the video. Do you guys know why you erase up and down instead of side to side? It's because when you erase side to side, your butt jiggles back and forth. OK, joke of the day. All right. So Ethan says, if you're going to insert for a stack and you want it to be fast, do it at the end. Why? 4, 2, 8, 1, 7. I'm going to insert there and pop, push and pop there. Why? What if we pushed and popped at the beginning? So it was a good guess. OK. Why do you think? You said, I think you said you showed it back there. Why? What happens if we push and pop at the beginning? Yeah. Yeah, if we pushed it right here, wouldn't we have to move 7 to here, 1 to here, 8 to here, 2 to here, 4 to here, and then put it there? And what would that behavior be? Asymptotically speaking. Linear, because you go through every one, right? But if we're clever about it and we just push it here and then pop it from here, what's the complexity? O1, constant, which is exactly like the holy grail of what we're looking for, right? We want constant behavior. OK, awesome. We can get the constant behavior. OK. All right, so the end of the array, order 1. Where should you insert and remove a linked list for best performance? In a linked list, where should you insert and remove? At the where? At the head? Sure. If you have a linked list, right, and you already know where the head is, how hard is it to put another node there? Put another node, change the head to point to this node, change the next to this one to point to where the head was, the other way around. Do it in the right order, right? And you would be done. What's the order of what's the asymptotic complexity of that? O1. How do we know it's O1 and not ON? It doesn't matter how many things are in the list. Did we look at this one, this one, this one, this one, this one all the way to the end? No, there could be a billion elements in there. Inserting at the head is an order 1 operation. OK, there was another answer to that. Yeah? If you have a tail pointer, you can do the same thing at the tail. Doesn't matter. If you're keeping a tail pointer, same idea. You've already know where the tail is, right? Inserting that other element is an order 1 operation. Done, right? OK, so you can do that. Awesome. So we've solved all the problems then. All of our data structures should be stacks because we can get perfect O1 behavior out of them, which is awesome. And we should just stop class and go home. Well, what are some downsides to using a stack? Let's see, somebody has an answer in a little bit. Yeah? You can only access the first one. Yep, that's definitely a big one. If I want to look at this one down here, how do I get to it? Yeah, pop, 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 then I get there. Top or pop, and I see that one. The other ones are gone. Right? You could put them in another data structure, and that's fine too, but you have to do all that extra work, and that's a pain. OK, what's another downside? Yeah, Graham?
Depending on how you've been using it, you do end up with a lot of wasted space.
Wasted space. I'm not so sure. I think a stack is a pretty good data structure space-wise. I mean, sure, a linked list in general is kind of a weird data structure, but if it's an array, you're doing the same thing as an array, so you're not wasting too much space. OK, but that's and by the way, the other kind of downsides are all kind of related to this idea that you have that you can't go anywhere but the top, right? So go ahead, John. You can't search through it. Yeah, there's no way to search through a stack, right? Unless you do the exact same thing and pop, 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 found it, right? No other way to search for it. OK, so those were 2 of the big ones I came up with. No random access, perfect, right? You can't walk the stack at all. There is no such idea of walking through a stack unless you're pulling the elements off and doing something with each one. OK? And of course, you can't search for it. So yeah. OK, those are definitely some big downsides. Yeah?
I guess, well, maybe we're going to get to this, but if we already know that it's just better to keep it on the constant order operation, what's the purpose of I guess boxing yourself into just using a stack rather than say using a dynamic array, but just making concerted effort to insert the most?
You can absolutely do that. You can absolutely do that. You can say, I'm only going to insert at the end and do that. Sure, that's fine. But generally, what we do is we have a stack class, so you already know. If I say, hey, create a stack for me, you know what has to be done, right? If I say create a dynamic array, you go, OK, well, I need to be able to insert in the middle. I need to be able to insert at the beginning. I need to be able to remove from anywhere. I need to be able to, and while I'm moving. For a stack, you go push, pop, top, is empty, done. Right? So it's simplicity in that sense. Yeah, a lot of these IDs are simplicity. And not only are they simple, but the number of things we want to do that fit into the stack mentality is actually larger than you might think. Like it turns out that there's a lot of LIFO type actions that we might want to do. So stacks are really good for that, right? So that's good. OK, so here's a stack example. OK, said I'd give you some examples of how we use this. This is one of the kind of a cool way to do this, or to use a stack. Let's say we have a program here. Now, anybody recognize this?
Lab 1.
It's what?
Lab 1.
Lab 1. OK. Here's what we're going to do with this. We are going to take this little section of code as input to our program. OK. And what we're going to do is we're going to check and make sure that all of the parentheses or curly brackets or square brackets are properly placed. OK? And what do I mean by properly placed? You can't have something like this. Let's say you had int main parenthesis curly bracket open parenthesis for some reason, and then closed curly bracket. Before you have a closed, is there any way this program could be correct? Unless this was inside quotes or something and it's a string. I mean, like there's degenerate ways that we would have to check. Like we're not going to worry about that here. But the idea is, as long as it's part of the program code, right? If you see an opening brace and then another opening brace and not a subsequent closing brace for that second one, and you find the other open or closed brace, you've got a problem, right? So that's one of the issues here. Well, guess what? We can use a stack to do this. OK? Let's see if we can come up with a method for using a stack to solve our little problem here. Ethan thinks he's got it. Everybody else think about it for 1 sec. Then I'll let you think about it. OK, think about how we would use this stack idea to see if we are correct or not. Hang on. To see if this is correctly parenthesized or not. Matched. What do you think, Ethan?
So the code gets read in as like individual characters.
Code gets read in as individual characters, yep.
They become like little pieces.
They become little like individual, yep. The I is one character, the F is one character, yep.
There's a number of conditionals that you would like ask, so like you find that first.
OK. All right, so let's start out. What do we do when we see the I? You ignore it, right? What do we see when we do the F? Ignore it. So we ignore anything that's not what?
Either parenthesis or a curly bracket or a bracket.
A bracket of some sort, right? OK, so that's good step 1. Read through the code, and when you get to a character that's not a bracket, ignore it. When you get to a what?
Bracket.
What kind?
Well,
Opening or closing?
opening.
OK, so let's say you get to a bracket. If it is an opening bracket, what do you do? What do you think? Steve?
An opening bracket, push it,
If it's an opening bracket, push it.
and if you find a closing bracket off, and then it's there, then that one should be off.
Almost. Yes, in fact, I went through this in the other class earlier, and I forgot this one little almost step, so I'm not criticizing you, but there's one extra thing in here. So yes, if you get to an opening, if it's an opening bracket, push it on the stack, right? End of story. If it's an opening bracket, push it on the stack. If it's a closed bracket, so you're saying, Steve, right?
Yeah.
Steve says, if it's a closed bracket, pop the one off the stack and check and see if it's what?
Well, I guess check first before you find.
Well, check first before you want.
Then that's only broken.
Well, kind of. What if our function was the following? Int main open bracket, or open parenthesis, or sorry, closed parenthesis. That's the first thing of our thing. We'd ignore closed. So then your method would be pop the stack or look at the top and say check. But what does the stack look like right at the beginning? Yeah, so we have to check if it's empty. Is that what you're going to say? You have to check if it's empty. So if it's a closing bracket, check if it's empty. But if the stack isn't empty, then I like your idea. What was it? pop it off, and then what? Compare it to the closing one. If it's not the same as the closing one, what? It's broken. So we're broken. We have an error. Or if the stack was empty when we had a closed one, it's broken. OK, so that's good. OK, and we keep going through. OK, we keep going through, and we find an open one. We push it on. We find a closed one. We check and see if it's empty. We pop it off, check. Da-da-da-da-da. We get to the end. We've finally gotten to the last one. And we pop it off the stack. Are we done? And we've got a good program? What do you think?
Oh, I have a question.
OK, what's your question?
When you say check to see, check the closing
Sure.
bracket, do you mean you compare it to what's the stack, or?
OK, if I let's do the first one here. OK, we're going to go through. We're going to ignore. We're going to get to a parenthesis, open parenthesis. We're going to push the open on the stack. OK, we're going to push the open one on the stack. Then we're going to keep going. Ignore the temp. Ignore the null. We're going to get to the closing parenthesis, and we're going to say, aha. We have a closing parenthesis. And you need to know that it's closing. You compare it, and you know the closing ones, right? So you see that, and then you say, is the stack empty? Nope. Good. Pop it off the stack, what's on there. Now we know, now that gives us back that when you pop it off the stack, it says, hey, that's a left parenthesis. Now can you check and say, if I have a right parenthesis, I'd better have a left parenthesis. If I have a right bracket, I'd better have a left bracket, et cetera. You see what I mean? So that's how it's going to be. OK, so going back to my question, you go through the whole thing. You get to the end here. One sec. Are you going to answer the question or have a question? OK, you get to the end. You pop this last one off. You check, or you get to the last one. You pop the first one off here, and you compare them. And are you done?
No, you have to check if you're empty.
Aha! You have to check if you're empty. Yeah. What if we got all the way to the end and we had an extra curly open on there? We would push it on. And then we'd be done, and we'd be wrong. So yeah, you have to check the empty. So you see how that algorithm works? OK, let's try it with this program. Ignore, ignore, ignore. Push on the parenthesis. Ignore, ignore. Get to the end of the null. Find a parenthesis. Pop this off. Are we good? Left and right. We're right here now. This parenthesis. Are we good so far? Yes, we're good. Then we get the next character is an open curly brace. If it's an open, that is a terrible curly brace. Holy smokes. There we go. We push a open curly brace on. And then we go do the return false, ignore, ignore, get to the end curly brace. What do we do? What's the algorithm say that we just thought up? Check, see if it's empty. We've got this one. What's next? Pop off, and then compare. Are they the same? They are, or they're equivalent, or they're opposite ones. So that's good. OK, so we're gonna skip. This is gonna be the exact same thing. We're gonna push the parenthesis on. We're gonna get to this one, push it off. Then we're gonna get to this one, which is a open curly brace. We're gonna push it on. OK, and then we're gonna keep going. And then what do we get to? An open square bracket. What are we gonna do? Push it on the stack. Boop, push it on the stack like that. Then we go along, and the next thing we get is a closed square bracket. We get a closed square bracket. What do? First check and see if it's empty. It's not empty. Then we pop, like I heard. Do they compare correctly? They do, et cetera, right? And then we do the same thing again here. It's going to be a push-pop operation there. And then we get to the final curly brace, and got a curly brace, check if it's empty, pop it, and they're good, so we're good. We get to the end of the file. Last thing we check is the stack empty? It is. So are we good? Is this a properly parenthesized program? It is. Woohoo! All right, so when we use the stack for that, pretty cool. OK, this is exactly what you guys told me. Empty stack, read the characters until file, opening symbol, push it, et cetera, et cetera. It's exactly what you just told me and what we just went through, which is great. OK? If the file is not empty, report an error. We went through this already. We actually did it on the board. Whoops, I forgot to change the color on this. OK, now, if the number of if the number of characters in this program are, hang on, I'm just changing the color here. If the number of characters in this program are n characters in the file that we're reading in, right? N characters. What's the asymptotic complexity of the algorithm on the previous page? This page right here. What's the asymptotic complexity of that? If there are n characters in this little code. This is a slightly different way of thinking about this asymptotic complexity. Ideas? Yeah.
Linear, because you read each character once.
Ah, I like that. It's linear because for n characters, we read this one, read this one, read this one, read this one, do a little stuff, but read this one, da-da-da-da, all the way through. We only need to read through it once for every character. That's absolutely linear. Now, the fact that we have used a stack, which is order 1 operations, doesn't really come into play except to say that we don't have to go through all the n characters. If it were for some reason we had to read up to the parenthesis and then like reread all the characters up to that for whatever reason, then that might be a different complexity. But the fact is, we just go whoop one time through the program and we can be done and do that. So it's linear. Kind of neat. Okay? Kind of a neat algorithm in that sense. Okay. All right, so we got that. Read through the file once. Again, that was a different way of thinking of the asymptotic complexity because the kind of the input was the n we were talking about. That's that. OK, so in the Unix tip of the day, we are back to that. We saw the DC calculator uses this thing called reverse Polish notation, right? Max called it RPN. Did I already say why it's called reverse Polish notation? No, it's called reverse Polish notation because there's this Polish guy who created Polish notation, which is the exact opposite of this, right? And so what people did was they said, oh, OK, here's a different way. We're going to call this reverse Polish notation because they called his method Polish notation. Right? Also called postfix notation. In other words, the operators are at the end. That's really what this means. OK, the operators, plus, times, divides, minus, all that, follow the operands, which are all the numbers. OK, so 3 plus 4 becomes 3, 4 plus, and that's what we showed earlier. Right? OK, here's an example. Did we do this one earlier? We might have actually done this one. 4, 5, 6 plus times. What happens is, OK, the plus acts on the previous two values. Okay? In other words, it acts on the previous two values. So when you get to a plus, you say, what were the previous two values? 6 and 5. Do that operation on them. So in this case, 6 plus 5 is 11. Right? This whole 5, 6 plus is now replaced by 11. 11 and 4, it goes 4, 11 times now. When you get to the times, what does it do? It looks at the previous two, which was 11 and 4, and multiplies them. I think we did a different one. I think we did a slightly different one. But yeah, in this case, we get 44, right? Because you do it in this operation. Aha! What's cool about this? We only need to read through it once. That's a linear operation. That's nice. Are there any parentheses in here? Aha! Right? No parentheses necessary for this. As it turns out, you don't need to know order of operations. All that stuff that your like 7th grade teacher taught you and banged into your head because PEMDAS and all that stuff, right? No need to know it now. Don't need it anymore, right? For postfix notation, doing arithmetic with this. Now, can you see something similar to what we've been talking about all day in this idea? 4, 5, 6 plus does these two, and then this gets replaced. Can you see how that might model something we've been talking about? Yeah? Rana? Like a stack, right? OK. What are we going to do when we hit this first number? Push it on the stack. What are we going to do when we hit the second number? Push it on the stack. What are we going to do when we hit the third number? Push it on the stack. What are we going to do when we hit the plus? Pop the previous two things off the stack and do the plus to them. Add them. Then what are we going to do? Push the result back on the stack. So now the stack is going to be 4 and 11. and and then we're going to keep going. And then when we get to the times, pull off the 11, pop the 4, multiply them, and then what do we do? Push the result back on, right? There's your algorithm. Okay, it's a pretty cool stack-based algorithm, right? 44, the plus x on the previous two values, the times x on the previous two values, and that's the idea. When you get to an operator, act on the previous two values, which happen to be the previous two things in the stack, right? Here's the method we just used. Read the input, push the numbers on the stack until you reach an operator. When you get the operator, apply that operator to the two numbers that are popped off stack. Not all operators need two things. There are some that need only one, like a minus symbol, which is an odd one to begin with because it only uses one and it acts on like a positive number. But for our purposes, for now, just think about just two operators or operands per operator. Plus takes 2, minus takes 2, divided by takes 2, all that. When you get done doing that operation, push that value back on the stack. When the input is complete, what's left on the stack is your result. That's cool. Like that's an easy way to do arithmetic. Yeah.
But you could theoretically have like a function that's way more complicated than like.
Oh yeah. Let's look at some. There's one. 6, 5, 2, 3 plus 8 times plus 3 plus times. OK. Max, you have a comment?
If I understood what you said correctly, so you meant like instead of having plus, you had something.
Yeah.
Oh, sorry, a
You
different
have
function.
like 6 inputs and then like.
Yeah, if you had some operator that took 6 inputs, you would know that you have to pop the last 6 values if you happen to do that. I mean, if you happen to come up with that. I don't know any arithmetic ones that need 6 operators, but yeah. But yeah.
Just like any.
Yeah, sure, anything. You could have some operator, yeah, sure, you could have some operator defined that way. Yeah, thanks, Max. Thanks, Ethan. OK, so let's look and see if this actually works. OK, I've got my stack here, right? Hopefully it's got enough values in it. Let's see if it works. What are we going to do with a 6? What are we going to do? Push. 6. What are we going to do with the 5, 2, and 3? Push, push, push. What are we going to do with the plus? Take off the 3 and the 2, pop those two, right? We're going to pop off the 3, pop off the 2, and we're going to add them, and we get 5. What are we going to do with the 5? Push it back on. OK. And then we're going to get to the 8. What do we do? Push the 8. We get to the times. Pop, pop. 8 times 5 is 40. What are we going to do? Push the 40. OK. And then let's see, plus. Pop, pop, 40 and 5. Right? And we get 45 when we add them. Then what do we do? Push it back on. Right? And then let's see, push. And then we push it back on for the plus. We got to the 3. Push. And then we get the plus. Pop 3 and 45, and we add them. So that's a 48. We get to the times. Pop, pop, 48 times 6. Anybody? 288. What do we do? Push it back on. And we're done with our input. What's our result? 288. OK? Cool algorithm, right? Also a linear algorithm, right? Also no need to like remember all that PEMDAS stuff. Your 6th grade teacher can retire now, right? This is probably not a bad way to teach arithmetic, as it turns out. Why they don't do it? Well, there's a lot of history behind like parentheses expressions, and it's maybe in some cases a little easier to like. Since you don't know it right now, looking at this, you go, what is it? But you can't really see where the groupings are as easily. I mean, there's some other downsides. Do you have a comment?
RPN calculators are expensive.
RPN calculators are expensive. You're not kidding. So where is it here? It's on a couple of slides. And I'll get to the RPN calculator bit in a little bit. You can actually buy RPN calculators, like calculators that use this methodology. In fact, the first calculators were this type of calculator. Hewlett-Packard and I'm not sure Texas Instruments did, but definitely Hewlett-Packard in the 60s and 70s came up with, 70s in particular, came up with calculators that used reverse Polish notation, and engineers like started learning it, right? You guys ever heard of a slide rule before? Yeah, if you ever watch the movie Apollo 13, you'll see all the engineers in there using these slide rules back and forth. That was before they had calculators. Engineers graduated, and it used to be that you could have, like, you'd carry around in your bag or whatever, a slide rule, right? Some people actually had belts that they would like put a slide rule in, and If you need to, oh, what's the square root of 8? Whatever, right? Kind of nerdy, but engineers like that, right? Well, when the desktop calculators came along, they all like migrated to those. It's so much faster than a slide rule, and they had to learn reverse Polish notation. And it's actually really easy. If you've ever once you get it, you're like, oh, that's pretty cool. I actually have a little reverse Polish notation calculator on my widgets up here, and it's hard to see I don't know if you can see. Yeah, you can see that down there. So there, I did the 288 earlier. If I did 3, 4, 5 times plus whatever, right? So you can do that. You can get them. So they're free if you do them on your computer, right? You can get them. You can still buy them. Okay. But this is so this operation it would have looked like this, and you could have parenthesized this differently and arranged them around. But I tried to do them in the same order. But it would have looked like that in infix representation, which is your normal representation, the way we think of normal. Okay, and you have to know order of operations. Now, in this case, yeah, you do have to know order of operations, right? You have to know the 8 times, this one comes before the plus and so forth, right? So fully parenthesized is this one. You can do it fully parenthesized, then you wouldn't necessarily need to know. Does anyone know why we have PEMDAS? Like why we care about order of operations? Any ideas? It's so you don't have to use all these parentheses, right? Once you know order of operations, you can get rid of a whole bunch of parentheses, and it makes the statements a lot easier. That's the only reason, really. I mean, other than that, you just parenthesize everything, but that gets ugly. So, all right. I should start the society to go back to RPN calculations. I don't think it'd go very far. What? You'll join? Awesome. We got 2 members. OK. Beauty of RPN, obviously no parentheses. It's cool, right? It's a perfect system for a simple calculator because it's so easy to program. This is why Hewlett-Packard did this, right? They were dealing with a computer that might have had like 80 bytes of memory or something, right? I mean, they're dealing with stuff that is like a very fixed small amount of memory, and to make it even reasonable to buy, reasonable being a very relative term, they wanted to do an algorithm that was pretty easy to implement, right? This stack-based algorithm, so simple. We just did it. We all figured it out right now. Okay. This is an RPN calculator from back in 1968. Okay, Wired magazine in December of 2000 called this the first the first desktop computer. Now it didn't have a keyboard and it had a tiny little display. And in fact, Bruce Mollet, who you might have met or might not have met at this point, told me that he had an older one of these, which is actually cooler looking. He told me about it. But this one, you could program it. It had special algorithms for trigonometry and logarithms and all that, right? But you could program it. It had loops, and it had the ability to write algorithms on this thing, and it fit on your desk. Hewlett-Packard actually called it a desktop calculator, even though it really was a computer. They decided in 1968, computer meant something as big as this room, right? And when Hewlett-Packard came out with this thing that was like this big, fit on your desk, they were like, well, if we call it a computer, nobody will take us seriously. So they just called it a calculator, and everybody's like, oh, OK, I'll buy one. All the engineers threw away their slide rules and got this, right? And so anyway, you could do this. Now, $5,000 for this little thing in 1968, which is about $34,000 today, right? You didn't get this unless your company was doing pretty well, right? You didn't have one on your desk unless your company was really either doing well or you absolutely needed it for your business, right? But very, very cool. And like I said, you can still buy them today in regular calculator form and get them if you want to. Okay? Despite what Max says, they're not quite as expensive as some of them are. But the graphing calculators are pretty expensive too. That's another. Do you guys ever get sick of the fact that you have to buy a graphing calculator which has a processor from 1983 in it and still costs $150? Honestly, a TI-83 should cost 18 cents, right? That's how much plastic is in it, and everything else is free at this point for Hewlett-Packard or for TI. Yeah, it's a little crazy, but they've got a market, and lots of high school teachers make their students buy it, so that's the way it goes. Oh boy, they tell you in slide making school never to put a font lower than 16. Here's why: you can't read this, right? And I don't expect you to. You can, using a stack, convert infix notation with all the parentheses and the notation we're used to postfix notation. That's what that BC calculator is doing kind of behind the scenes, right? The BC is converting that long expression with the parentheses in it to an expression that DC, using RPM, understands, and feeding it to DC and saying, please calculate this for me. That's all that BC does, as it turns out. Or at least it used to do. I don't know what it does these days, but that's that. But here's a big, long algorithm. You can follow this. Last semester, I made a rookie mistake of trying to actually do this like with a big expression and got so mired in the details it was ridiculous. But you can look at this at your leisure and try to implement it if you want. OK, I do have to come up with a stack/q homework assignment, so you never know. Might go on there. This would actually be a pretty easy assignment. It's like follow the rules. All right, that's how easy this one is. OK, all right. So we've got the postfix notation, and we've got this infix notation. We've also got prefix notation, which is the Polish notation I talked about earlier. This is the one that guy designed and got it named after his country, right? Okay. This is the one where instead of the operators coming first, the operands coming first, the numbers coming first, they do the operators first, right? And you do times, minus, then you do 5 and 6. And I believe when you get the 5 and 6, then you do the minus. And then that goes back on the stack. And then you get the 7, and in this case, the -1. And then this would be -7. OK, so it's the same idea. You could do it with a stack. In this case, what would you be pushing on the stack? The operators, probably, right? You'd push the operators on, and then when you get to 2, you'd probably have to somehow keep track of how many operands you've gotten to, and then pop 2 things off the top. And it might get a little ugly, but you could still do it with a stack. OK, we will see this again. We'll see the postfix, prefix, and infix ideas again when we talk about binary trees, which we'll get to in a couple weeks. Binary trees and walking through a binary tree. You can do this in a bunch of different ways. You can do it either going post order, meaning you go to nodes, and when you're about to leave a node, you print it. You could do it in prefix order, which means you go to a node, you print it, then you go on to the next node. Right? And you can do infix, which is saying, well, sorry, it's kind of the other way. Yeah, infix says, go to the node, it's like follow-on nodes. When you're kind of halfway in the middle, then print it out. We will see examples of this. We'll do a whole lab on it. And you'll see like the different values of this. But that's the idea. OK? Questions on stacks at this point? Not a very hard idea, right? Like stacks aren't too hard to understand. OK? The last thing I want to do is just really quickly put down the C++ for the interface. This is actually going to take like 1 minute, right? For push, what is the function going to look like? Not the actual code, like the function declaration. To push something on the stack, what's it going to look like? Max? Return type void. When we push something on the stack, we don't care what, like nothing needs to come back. Good. Or Boolean if we run out of stack space or something. You could certainly do that. You could say push, but if somehow you run out of stack space, return false. Could do that. Let's say void for now. Push, and then what? Yeah, whatever type of value you're using. If it's a card, or if it's a string, or if it's an int or whatever, some type there, and then we'll just call it, I don't know, v for the value, right? That's how you're going to do push, and you're going to implement that in your dynamic array or in your linked list or whatever. OK, what about pop? What's pop going to do? Yeah. Return type whatever you're using. In this case, we'll do int, sure. Then what? Pop. Then what? Nothing, right? You don't know what you're going to get. I mean, like, there's nothing to pass into it. You just say, give me what's on the top of the stack. OK, what about top? Top actually tells you what the peaks at the value and tells you what it is. So it's int, same thing. Int top. Anything to send to top? No, right? It's the same ideas. In this one, though, you actually take it off the stack. In this one, you just return it and show what it is. Okay? It's in the C++ stack implementation, if you end up using that, what they do is they say pop takes it off, but it returns a void, right? And then top actually returns an int. So if you want the value that's on the top of the stack, first you do top, then you do pop. It's I don't like that they do it that way, but there's actually a good reason that I read on Stack Overflow, and I said, oh, all right, I'll buy it. But that's what you have to do. Yeah.
How does it compare to how it's implemented in x86? Are they trying to mirror it?
They're not trying to mirror it. No, in x86 it actually pops up and gives you, well, it puts the value in a register, so it does put it there. It does move it into the register, yeah. But no, they do it for it's an object-oriented kind of reason where they say you could, if you do pop and it returns the value, maybe there was an error, so it has to return something, and what do you return? And I mean, it gets kind of ugly like that. So they've got a reason why they do it. But in that instance, top then pop, and you'll be fine if you want to take it off the stack. Okay, so that's that. Well, there's one other, is empty. What's is empty going to do? Boolean, right? Bool is empty, right? Like that, and it's just if it's empty or not. You have to keep track of whether or not the stack's empty, right? Like under the covers, you have to know, have I put anything on there? And your dynamic array already does that for you. Your linked list might not. Your linked list might not, but you could easily check and see if it's null, right? If the head is null, it's empty. That's that, OK? You can do that. Do I ever need to count how many items are in a stack? Not explicitly, not for the interface. Could care less, right? Under the covers, sure, you have to know, but in general, you have to know. But as far as the interface is concerned, nope, don't even need to worry about it. OK? All right. So that's that. Other questions on stacks? Yeah. Sorry, hang on, guys. Ah, yeah, that's a very good point. When you pop something under the covers for a dynamic array, 672, if the top is here, popping returns a 2 to you, and then top is now here. And you don't care to delete that, right? If it's a linked list, yeah, you'll delete the top one off the head. But in an array, you don't bother. Other questions? All right, see you guys Monday.
So I didn't
Yeah.
call like x86 or any ASM implementation of the stack, because you can modify the stack.
Yeah, you can.